And my pleasure to welcome one of our rockstar speakers, Deputy CTO at Zoo, Java champion, GCP executive committee member, and just a Java pioneer, Simon Ritter.
Hello. Right. Yes. Welcome.
Well, Simon. Yeah, sorry we've been late a bit with like previous talks. So if you can maybe have your talk a bit shorter, that will be probably great to get back to the schedule. But yeah, I mean, I'm very happy to have you with us today.
Okay. Great. Well, what I'll do then is I'll get started straight away, and I will endeavour to bring my presentation in just a little bit. I do have quite a lot of information to cover, so hopefully I'll be able to get through all of it in the time that I've got. Right. So the presentation I'm doing today is about, as the title says, the art of Java type patterns. And what we're talking about here is a new feature in terms of the Java language that's been added, but patterns have been around for actually a long time. I mean, you can trace the basic idea of pattern matching in programming languages all the way back to the 1960s, really about the time that programming languages really took off. And if you look at languages like Haskell or Awk, you'll find that pattern matching is used in these things very much. Now, what do we actually mean by pattern matching? We're not talking here about pattern matching in the sense of regular expressions and using the pattern class that we have in Java and matching class that we have in Java. It's more at a fundamental level in terms of the programming language itself. And we'll see how this works as we explore the different features that have been added to the language. But what we need to understand is basically, what do we mean by a pattern? And in this case, there's two parts to it. So we have what's called a match predicate, and then we have 0 or more pattern variables. So a match predicate is essentially something that we're testing against to see whether we match that specific pattern. If we do match against the specific pattern, and we've got a target that we match against, then we're going to determine which variables we need to conditionally extract, make available to you as a programmer, and then you're able to use those in your application code. So that's the fundamental idea. And what we'll see as we go through is how that actually works in practice. But essentially, what we're looking at when we look at patterns is two parts: the predicate and the pattern variables. Now, there are many types of patterns that we can use. So let's talk through what those are in terms of the way that we can use them. So the first of those is a constant pattern. And we already have those in Java, because you can look at the switch statement and you can see that what we're doing is we're matching against a constant. That's the idea of a case statement. So we have case 1, case 2, case 3. Now, because that's our pattern, case 1, we're trying to match against 1 or 2 or 3. That's our predicate. We don't need a pattern variable because it's a constant. So there is no variable, so no requirement to have a variable because it's constant. The second type of pattern that we can use is a type pattern. Java is an object-oriented language, so we have classes, we have a type hierarchy involved. So we can match against a specific type. That's our pattern that we're looking for, and then we make variables for those given types. The third one is a deconstruction pattern. So we match against the pattern predicate, and then not only do we make a variable available associated with that pattern, but we also extract information from the pattern that we've got. And again, I'll give you examples of that as we go through, and you'll see exactly what I mean by that. Another one that we can use is a variable pattern type, and that's where we're going to use type inference. If you think about JDK 10, we introduced the idea of local variable type inference. Rather than having to define a local variable as being like an array list, you can simply say var l equals new array list, and the compiler can infer from what we're actually creating, what we're instantiating as an object, what the type of the variable is going to be. We can apply the same thing in terms of our patterns. The last one that we're going to look at is what we refer to as the any pattern, and this uses the underscore. So what we're doing there is we're matching against anything, but we're not binding to anything. We're binding to nothing. Again, probably easier to explain that later on when we show an example of that. But just remember that we're matching against anything, but we don't need to bind to anything. Right, so before we get into the details of pattern matching, there are a couple of things that have been added to Java more recently that we need to talk a little bit about first so that we can help in the understanding of how pattern matching applies to those features. First of those is switch expressions. So these were introduced quite some time ago now and have become a full part of the Java language. Switch expressions is a modification to the existing functionality that we had right from the very beginning in Java, which was the switch statement. Switch statement is very useful. It's effectively a multi-if then else construct that we can use to determine based on a value what we want to do. The problem with the switch statement is that it has certain design features which make it quite error prone. And that's really as a result of the fact that the syntax of the switch statement was taken directly from the C programming language. The reason for that was that the developers of Java wanted the syntax to be familiar to programmers who'd already used C, so the idea of moving to using Java was going to be fairly straightforward for them. But because C is a systems programming language, it's really designed for operating systems and compilers. Some of the way that things like the switch works is not necessarily intuitive to developers and also can lead to errors. Most obvious of those is that for each set of case statements you have, you as a developer must remember to put a break statement in. Otherwise, the way that it's designed to work is it will fall through to the next set of case statements and then execute whatever's associated with those. And that can lead to quite hard to find bugs because you think, well, can't possibly do that piece of code because I'm getting this value, but because you forgot to put a break statement in, it does that. And so you don't necessarily figure out how that works. So what we have with the switch statement is a very common way of using it. Let's look at an example here. The common way of using it is to say we're going to switch on one value, which in this case is the day of the week, and then we want to assign a value to another variable. In this example, it's number of letters. And as we can see, the code here is quite verbose. There's quite a lot of code. What we're doing is we're saying switch on day, and then we have case Monday, case Friday, case Sunday, and we assign the number of letters to be 6. And then we remember to put our break statement in. If we forgot that, we drop through into the Tuesday and we set the number of letters to be 7, which is why I say that that can be quite hard to debug. Now, obviously, aside from the putting the break statement into all of our blocks of cases, the other thing we have to remember is to assign a value to number of letters. If we don't do that, and we're using an instance field rather than a local variable, the compiler will be quite happy with that. It will simply say, well, number of letters by default is 0. If you don't want to set it to a different value, I'm not going to complain about that. That means that if you forget to set the value, again, it can introduce some problems in terms of debugging and hard to find errors. So let's look at how we can do that with a switch expression. So a switch expression is now allowing us to say, not only are we going to evaluate what is happening in terms of the value of day, but we're going to assign a value that we can return from the switch. So we're returning a value and we can assign that. The code here is rewriting that using switch expression, which was introduced in JDK 12. Immediately you can see that there's a lot less lines of code. And this is good because we've eliminated a lot of the sort of verbosity of that and the boilerplate code. But we haven't lost any of the readability, and that's the really great thing. Let's kind of break this down. So the first thing to see is that because it's now an expression, we can assign the value to number of letters with a single assignment. So we take the result of the switch, assign it to number of letters. That means that we don't have to remember for each of those cases to assign the value ourselves. If we look at the way the case statement works now, we've enabled the use of comma-separated lists, so we don't have to have each case separated with case Monday, case Friday, case Sunday. That to me is one of the most powerful things of this changing construct, is that ability to put things on a single line. We've then used the syntax from lambda expressions, borrowed the arrow operator, and what that says is that the right-hand side of the arrow operator is the value that will be returned from the switch expression. This is, again, powerful because, one, we don't need to have a break statement for each of those, so we don't have to worry about remembering that, but also because we have to return a value on the right-hand side, or throw an exception, the compiler can check that for us. So the compiler can make sure that for each of those case blocks and the default, we know we definitely have a value that's being returned or an exception that's being thrown, so there's no missing a particular value there. So this gives us a much more powerful way of expressing things with switch. Now, one of the important things about switch expressions is they must be complete or exhaustive, and we'll come back to why this is important later on. The other thing we need to talk a little bit about before we get into the pattern matching is algebraic data types in Java, which have been added more recently. Now, Java, as I said, is an object-oriented language, which means we have encapsulation. We have the idea of a class, and if we want to create a very simple class that just stores two values, this is what we end up doing. We create a class called point. Then within that class, we have to define what we're going to store. In this case, it's two double values, x and y. We'll make them private because we want encapsulation, and we'll make them final as well. To initialize those values, we need a constructor. So we define that. Public point takes two values, two parameters, double x and double y. And then within the body of that, we have to explicitly assign the values of x and y to the instance fields of our class to make them available. In order to access them, because we have made the values private, we need accessor methods. So we'll define two methods, both of which return a double and are called x and y, and simply return the values of x and y. That is 14 lines of code just to create a tuple in Java. Now, I would say that it probably would have been easier if we had introduced tuple as a class into the standard libraries. And I did ask Brian Gertz about this, but he said, well, if we create a tuple for you, then you'll want a triple, then you'll want a quadruple. And where do we stop? And that's a very kind of sensible analysis of the problem. What we now have, rather than creating a tuple class or a triple class or whatever, is the idea of a record. This is a much more generic solution to the problem and is a much better way of doing it. Rather than writing all those 14 lines of code, what we can now say is that we want a record called point, and we'll give a record definition, which is the same syntax as the constructor, and that simply says which values do we want to store in this record and what type are they. So in this case, our point has two doubles, x and y. Now, a record is just like a class. It is a class, in fact, but it's just a special form of class. You can think of it the same way that enumerations are a slightly special form of class. Because of that, the record can have a body, which we can include between the braces. Because our point doesn't have anything beyond simply storing those values and making them available, we don't put anything in the body, so we can reduce this to a single line of code. Now, because it's a class, we can provide all the sorts of things that we do with other classes. We can make them generic if we want to. So we can specify a type parameter, and then we can have anything of type T, and we can store objects of type T in that record. And that means that we can store objects of any type that we want when we use that record. The other thing is that because we have a body associated with the class, if we want to, we can add additional functionality. We can't add any additional instance fields that aren't defined in the record declaration. In the case of our circle, we've got a single value, the radius, and we can't add any instance fields beyond that. But we can add static fields. So that's fine, we can add those. So in this case, I'm adding a value for pi 3.142. And we can add additional behavior in the form of methods. So now I've added a area method that returns a double, and that just takes our static field pi, multiplies it by the radius squared, and returns the value. A couple of other things to be aware of with records, this is important, is that the base class of all records is the java.lang.record class. And so what that means is that you can't subclass, or record cannot subclass another class because it already inherits directly from record. If you want to, you can provide as many interfaces as you like. As long as you implement the methods associated with those, that will work quite happily. The other thing about records is that they are implicitly final, meaning you can't inherit from a record. If you want to, you can add the final modifier to that, but it doesn't have to be done because it's implicitly final, so the compiler will do that for you. And then the last thing to be aware of is that records don't follow the Java bean pattern. Java bean pattern says that for values that you're storing in a bean, you have a set of methods for accessing and changing those. So you get x as a example in our point that we have. You would have a corresponding set x method in that to change the value. Now, in a record, all of the values that you're storing in the record are shallowly final, meaning that or shallowly immutable. All of the values that you have in that record are marked as final by default. In the same way that the record itself is final, all of the values are final as well. I say shallowly because obviously if you have reference to another object, the reference to the object is final, but the things in that object can be changed if you want to, if it's possible to do so. Now, what that means from an accessor method point of view is that it uses just the name of the variable, not get followed by the name of the variable. That did cause a few problems initially because some people have used the bean pattern extensively. If you look at things like Spring Boot, for example, that used the bean pattern, and so it was a little harder to use records to start with. That's now all been solved. Spring Boot now is fully adapted to use records. But as somebody pointed out to me, that if that was a real problem, what you can simply do is name your variables, get x and get y. That way you still get a get x and a get y accessor method, and everything will work as you expect it to. But it's not really recommended to do that. The other thing to be aware of is that in Java we have inheritance, it's object oriented, so we can define a type hierarchy. Now in this case I've declared a superclass called shape and then 3 subclasses, triangle, square and pentagon. The thing about this is that we don't, as developers, have any real control over who can inherit from any given class. The only thing that we can do is mark it as final, and that will prevent anybody from inheriting from that class. So it's an all or nothing approach. Either everybody can inherit from it wherever they want to, or nobody can inherit from it. So what we've introduced in JDK 15 is the idea of a sealed class. Here we can make our shape class sealed. We introduce a new modifier for the class definition. So we say public sealed class shape. And then we add to that a permits clause, which will list all of the classes which are allowed to extend shape, in this case, triangle, square, and pentagon. And that limits the classes that are able to inherit from that. If somebody were to come along and say, oh, I like your shape class, I'm going to use that as my superclass, and I'm going to create a circle as a subclass, the compiler will look at the permits clause and it will say, no, circle is not listed there, and it will give you the error message to tell you it's not allowed to extend the sealed class shape. It's not listed in the permits clause. Now, when we look at the inheritance of the classes that inherit from a sealed class, all of those classes must have their inheritance capabilities explicitly specified. What do I mean by that? Well, there are 3 ways you can do that. The first is that we can continue to make our class sealed. So we take our class triangle, we have to specify its inheritance capabilities. So we say that it is a sealed class triangle, and it's going to permit 2 further subclasses, equilateral and isosceles. The second thing we can do is we can mark it as being final. So we'll just say that this class square can no longer be inherited from anybody else. It is final, so that's it. And then the last thing that we can do is we can use this new modifier, non-sealed, and that will effectively turn off the sealed nature of that class. Anybody will then be able to extend, in this case, pentagon. This is kind of interesting because this is the first hyphenated keyword in Java. And there was a lot of discussion about whether we should use hyphenated keywords or not. And the eventual decision was that because we may well want to extend the language a lot further in the future, to not limit ourselves, we will use hyphenated keywords. The other thing that's very important about this is that these are contextual keywords, meaning they only act as keywords in that position in our code. And there's a very good reason for that, because obviously if we had sealed, for example, or permits as reserved words, in the same way that class is a reserved word and public is a reserved word and so on, we wouldn't be able to use them as variable names. And that could break a lot of existing code, because I'm sure that people have used sealed as a variable name or permits as a variable name. The other thing with the hyphenated keyword is obviously we could create 2 variables, one called non, one called sealed, and then we could say sealed equals non-sealed. And if the non-sealed was working as a reserved word, we wouldn't be able to do that, and that wouldn't make any sense because, of course, that's a mathematical evaluation, not a keyword in use. Right, so having looked at the fundamentals that we need to be aware of, let's look at what we have in terms of pattern matching in Java. Now, the first thing that we can apply pattern matching to is instance of. If we look at the way that the instance of operator works before we introduce pattern matching, this is very much what we're going to see. We say if obj, our reference to an object, is an instance of string. Java, being object-oriented, also has the idea of polymorphism. We can view an object as any of the classes or interfaces that it is or implements. So whichever is the concrete class that it is, any of the superclasses of that right the way up to object, and any of the interfaces that it implements, we can view that object in that way. If we get a reference to an object, we may want to determine if it is one specific type, and that's why we use instance of. We're all familiar with this, we've used it many times. So we say if obj instance of string. Now, if we want to use that reference because it is a string, we can't just use obj. That would be nice, but it's not the way the programming language works. To do that, we have to create a new variable. In this case, we're going to call it s. We have to declare that it's of type string, and then we have to do an explicit cast to say that the object reference we have is going to be a string, and we cast it to a string and assign it to string s. And then we can reference that and we can print out the length. Now that's a little bit more work than we would really like to do, because obviously every time we want to use instance of, we have to do this explicit assignment and we have to do the explicit cast. So it's just an extra line of code that we don't really want to do. What we can do, this is introduced in JDK 14, is introduce the idea of pattern matching for instance of. Now, remember when I spoke about patterns at the beginning, we have the pattern predicate and then we have pattern variables. In this case, the pattern predicate, what we're going to test against is obj is an instance of string. That will evaluate to a Boolean, so we know true or false, is obj a reference to an object of type string. If that predicate matches, then we have a pattern variable that we associate with that, which is s. And s will then be assigned the reference to obj, and it will be treated as a string. That way, in the true branch of our if statement here, we no longer have to make the explicit assignment, the explicit cast. We can simply say print out s.length. And because s is a string, we know that we can use it. Now, importantly, obviously, if we don't have an instance of string, the false branch will not have a reference to a string, so we couldn't use s there. The pattern variable will be invalid at that point. We can take that a little bit further, and we could add an and to our test, and we can say if object instance of string s and s.length is greater than 0. This will work because we know from the way Java works that the and operator, we always evaluate the left-hand side of the operator, obj instance of string, and if that evaluates to true, we will evaluate the right-hand side. Now, if the left-hand side evaluates to true, we're matching our pattern predicate, so we can have a pattern variable s that becomes valid in terms of its scope, and that means that on the right-hand side of the and operator, we can reference s, and we can call the length method on it and test against greater than 0. If we were to try that with the or operator, that wouldn't work. In this case, we always evaluate the left-hand side of the operator, but only if that evaluates to false do we evaluate the right-hand side. If we evaluate to false, we know we don't have a string, s scope will not be valid, and therefore we can't call the length method on it, and the compiler will reject it. Now, the other thing about the way that we do the pattern matching and the assignment of the variable and the scope of the variable is that we can invert that test. We could do something like this. We could say if not O instance of string s, then we return from this method. Because that's an inverted test and we're saying that's the false branch, so the false branch is to return, the effective true branch of that test is everything after the return statement. So all of the rest of the code in that method. In that case, the scope of S is going to be valid for the rest of the method. We don't need to put it inside a true branch. We know that we could use s.length right after we've made that evaluation. We could have several hundred lines of code and we can still use s.length later on. Now that brings us to the idea of how scoping works for our pattern binding variables. And it's a little bit different to the way that scoping works for local variables. Local variables, if you look at the definition of how their scope works, is it's from the declaration of the variable until the end of the block in which it's declared. So that means that the end of the code block, the end of the method, the end of the for loop or while loop or whatever. That's the scope of local variable, and we're used to that. The other thing that's important about local variables is they're subject to definite assignment, meaning that you have to assign a value to the variable. It doesn't have a default value like an instance field. And if you don't do that, the compiler will give you an error. Binding variables work a little bit differently. So binding variables are subject to definite assignment. They have to be assigned a value, but the scoping of the binding variable is all the places in the program where you will have definite assignment. So in the case of the previous example, if obj instance of string s, the true branch of that is the place where we will have definite assignment because we do have a string. This is what we call flow scoping. Flow scoping is not the same as for local variables, which is actually good because we can do something like this. We can say if O instance of integer, that's our pattern predicate, and then we're going to assign it a pattern variable called num, and that scope of that will be in the true branch of that if. We can then have an else if in O instance of float. Again, predicate, their pattern predicate is O instance of float, but we can use num as the pattern variable because it's not going to clash with the one that we have in the original if statement. The scope of it is only where it is definitely assigned. So if we have an integer, it will be definitely assigned in the first part of the if. If we have a float, the definite assignment will be in the second part. And if we have a long, the definite assignment will be in the third part. That way we don't have any problem of overlap and we can reuse the variable name without having to worry about that. This is really good because it means that we don't have to think of like many variable names in this case, and we can do num rather than num1, num2, num3. Now, here's a little puzzle for you. Will this work? Let's say we assign a new instance of an object and we assign it to a variable that's called s. We then do if s instance of string, so that's our predicate, s instance of string, and we'll reuse s as the pattern variable. If it is a string, we'll print out length of string of length, and the length of the string. If it's not, we'll print out no string. Now, if you run that in Java-C and you try to compile it, you'll get an error. If you run it in JShell, in fact, I should have changed this, is version 21. In JDK 21, if you run that, it will actually run and it will tell you no string. I have no idea why this works. Nobody has yet been able to tell me why this works in JShell, but it doesn't work in Java-C. Very logically, it doesn't work in Java-C. I wouldn't expect it to compile, but in this case, using JShell, it will compile and it will run and work. I don't know why. Anyway, moving on. Next thing we can apply pattern matching to is switch. If we look at the way the switch worked previously, we've had the idea of only being able to switch on a limited number of things. We can switch on integral values, we can switch on strings, and we can switch on enumerations. What we've now done is extend that so that we can also switch on a type pattern. So remember I talked about the different pattern types that we have, and one of those is a type pattern itself. We could do something like this now, and we can say type tester takes an object reference, and then we switch on O, and we can do various things in terms of the cases and the default. First one we're going to have is case null. Now, this is a new introduction to be able to do that, which is very sensible, and I think it's a really good new feature. Previously, if you had a switch on something that was like this, providing a null would have given you a null pointer exception. But now what we can do is have a case for that rather than having to do an explicit if outside of the switch. Case null, we don't have a pattern variable because it's a constant. Null is null is null. And we can simply print out we've got a null type. For a string, our pattern predicate is going to be case string, and the pattern variable is s. It's kind of the same as the if instance of way of doing things. In this case, we'll print out what the string value is. Same with color. If we've got a color, we've got a pattern variable C. We can use that on the right-hand side, and we can print out the RGB value of that. Primitives in Java are not types, so we couldn't have a case for int or a case for byte as a primitive value, but we can for arrays of those. So arrays of objects are still a type. So even if it's a primitive, we can do case int array. We'll use a pattern variable IA, and then we'll print out the length of that array. And then we'll have a default if we've got anything else. Now, a couple of things about that null. Null is special. So we can use now case null, which is effectively used in all switch statements and all switch expressions. That doesn't mean you have to include it in every one of them. You don't have to go back and change your code to match this idea that all switches must include a case for null. The compiler will do that for you if there isn't one there. And what we would see is something like this. So we've changed our type tester. Now we've got switch on O, case string, case color, case int array, default. If we passed a null into that, what will actually happen is that the compiler will add in an extra line for us. So we'll have case null, and it will throw a null pointer exception. That means that even though every switch has to have a case for null, you don't have to explicitly state it, and the compiler will add it, and that doesn't break backwards compatibility. The other nice thing is that we can have a situation where we can deal with null and default at the same time. If we want to deal with anything that isn't in our set of cases, that includes both null and everything else, then we can do this. We can have case null, comma, default, and then we can print out, oh, we got a bad input, but we don't throw a null pointer exception. That's a nice idea that we've got that extra flexibility that we can deal with both null and default at the same time. Now, completeness, I kind of mentioned this when we talked about the switch expression. So pattern switch statements and all switch expressions must be exhaustive, which means we have to handle all possible values. Again, let's take our simple type tester example here. We'll pass an object reference to it, and then we'll do switch on O. We've only got two cases here, one for string and one for integer. Now, what happens if we pass a float to that method? Well, obviously there is no case for float, so the argument could be that because there is no case for it, we simply ignore it and we bypass the switch and we don't do anything, we return straight away. But that would potentially lead to a lot of errors because people might think, oh, I forgot to put it in, and it would be better to have the compiler check for that. So the decision was made that all possible values must be dealt with, which means that you can't have a situation like this where you've got just string and just integer. To solve that, a very logical way of doing it is simply to add default, because with something like object, obviously there's an infinite number of types that we could pass to that, so we can't have an infinite number of case statements. We can have a case for string, a case for integer, and then everything else is handled by default, exactly the same way that it works at the moment, so we're very used to that. What this doesn't mean is that we always have to have a default. This is why we come back to one of the things I talked about earlier when we talked about algebraic data types in Java. We can use our type tester on shape and use that sealed class that we had in the previous example. Now what we can say is we have a shape that we're passing in, and then we say switch on shape, and then we've got case triangle, case square, case pentagon, case shape. That means that we are complete because there is nothing else in that type hierarchy that can exist. We can only have triangles, squares, pentagons, and shapes. Now you might think, well, hang on, triangle was something that also was sealed and it had two subclasses, which was equilateral and isosceles. But remember, those are both triangles. So they will be caught by the triangle case. We don't have to explicitly state them. They don't have to explicitly catch them, but if we wanted to, we could. But in this case, because we'll catch them as triangles, it is complete. Similarly, shape itself is not an abstract class, so we need to have a case for that to ensure that if you define a shape on its own, that is also caught. Now, what we can also do is we can use that idea that we had before where we can add an and to this. This is called a guarded pattern. Now what we can do is we can extend that and we can say case triangle T, and then we use a new contextual keyword when and say t dot area is greater than 25. Now in JDK 18, they use the double ampersand, same way that we did with the instance of earlier on. They decided they'd use that originally, but then in JDK 19, the developers switched to using when. This is something you can argue both ways. I actually think it would have been better to continue using double ampersand, and we'll see why a little bit later on. But they decided that this was more readable, so we now have case triangle T when t dot area is greater than 25. So we've got a test on that. Now, in order to be complete, we also need to have a case for triangle on its own. That way, if we do have a triangle which doesn't have an area greater than 25, we won't match on the first case. We need to catch that triangle further on. Technically, you could also argue we don't need that because we would catch it in the shape class at the end, but I just put that in there for completeness. Only works on patterns, so you can't do, for example, case foo with a string when something else. So it will only work with the typed pattern. Now, where when is important. So we have this contextual keyword, which means that it only behaves as a keyword when it's in a certain position. What do I mean by this? Well, let's create an example here. So let's create a sealed abstract class called interrogator, and it's going to permit 5 subclasses: who, what, where, when, why. Okay. Then we're going to define our when class, which extends interrogator, and we will say that that has a Boolean method called when, which returns true. What we can then do is we can create a method like this. We can say public void test question, takes an interrogator as an object that's being passed in, and then we switch on the question. And I haven't filled in all the cases yet, but we can have cases for what, we can have cases for where, and we can have cases for why. In terms of the pattern variables, we can use the same name with a lowercase as the name of the class. So we've got what, where, why, and then print out all of those things. And then we can have a default, which technically I don't think you need because I don't know how you would get to that point, but I've added it there just for completeness. And we can add a couple of local methods, one which is called where and one of which is called why. That then allows us to add another case, which will be who, what, when, where, why. The reason we can do this, obviously, is that the pattern that we're matching on is the type who, with an uppercase. We're going to give it a variable name, pattern variable, which is what. We're going to use when to indicate we've got a guarded pattern. And then we're going to call where, local method, to determine whether that guarded pattern matches. And then we're going to have a call to why, if we match on that. And then we can go even a little bit further than that, and we can say case when, when. The reason we can do this is because of that contextual keyword, and the compiler can actually amazingly figure out what we mean by this. I really don't recommend doing this as a piece of code, but let's just look at that. So we say case when, first when, obviously with a capital, is the type that we're interested in. We're going to give it a pattern variable, which is when, and then the second lowercase w when is the contextual keyword to indicate that we have a guarded pattern, and then we have a reference to the pattern variable when, which we will then call the when method on that variable, and then if that matches, we'll call the local when method. As I say, it's not a very sensible idea to write code like this, but I just wanted to show that it is possible to do this, and the compiler can still figure out what you mean by that code. Pattern dominance is also very important. So what we need to make sure is that a less specific case doesn't hide a more specific case. Again, going back to our type tester example, if we change the order of that and we put the shape at the top, because shape is the superclass of all those lower classes, in the same way that triangle will catch isosceles and equilateral, shape will catch triangle, square, and pentagon. And that means that everything that you pass in will only go through the first case. And the compiler will reject that, and it will say that, case is case of shape is always matching, and so the other three cases are unreachable. It will never get to them, so the compiler will reject that. Similarly, we need to be careful when we're using a guarded pattern. So if we have this example where we've got case triangle on its own, and then we have the case triangle t when t dot area is greater than 25, because any triangle would match on the first case, we would have a situation where the second guarded triangle reference is unreachable, and so the first triangle reference is dominating the second one, and so the compiler will reject that because it's not valid and we've got an unreachable code. However, we need to be careful when we're doing that, because it doesn't mean that we must always put the guard above the unguarded reference, because if we did something like this, which I don't know why you would do that, but you can technically do it, case triangle t when true, that will always dominate the case triangle t on its own, and so that would again be a pattern that's dominating the unguarded pattern, and the compiler will reject that. So the way this works, and if you look at the specification for it, it says it is a compile time error for a label in a switch block to be dominated by an earlier label in that switch block. And that's effectively just what I've spoken about, the examples I've given you. So you must have a situation where you don't dominate a lower block. Pattern matching for instance of records. Okay, so we've talked about records and the idea that we have these algebraic data types in Java now. We can do pattern matching on a record. So we could take our existing point that we had, and then we can create a Pythagoras method. That takes an object reference, and then we're going to do a pattern matching on instance of, and we'll say if O instance of point P. What we then do is we want to extract the values from that record, and so we'll do double x is p dot x, double y is p dot y, calculate the hypotenuse by doing the square root of x times x, y times y. We can do better than that. So we'll introduce the idea of record patterns, which came in JDK 19. So this is what we call a deconstruction pattern. Again, going back to the pattern types that we talked about earlier, one of those was deconstruction pattern. Now, deconstruction patterns only work with records. You can't use it with a standard class, only records. And how that works is we can do this. So we can say Pythagoras takes an object reference, and then we say if O instance of, but rather than just saying point and giving it a pattern variable P, we actually give it the full definition or the declaration of the record. So we have point, double x, double y. One important thing to note about this is that it doesn't have to match the declaration of point that we had earlier, but only in the sense that we don't have to use the same variable names. So we could have point double like j and double I, for example, if you wanted to. But so long as the signature of the record matches, so you've got two doubles, then it'll work. And that way we don't have to then extract ourselves the values of x and y by calling the methods on that. The compiler will do the deconstruction for us, so it will make x and y pattern variables, make those available in the true branch of that if statement, and then we can simply do square root of x times x, y times y. Now, patterns are composable in terms of records. So let's take the idea that we've got an interface called rectangle. We've got a record point like we've had before, and then we'll introduce an enumeration of color, red, green, blue. Now what we can do is we can create a couple more records, first of which will be a color point. So that's going to have a point in it and a color. And then we'll call a color rectangle as a record, which is going to have two color points, top left and bottom right. And we'll just implement rectangle because it's going to be easier for my example. So then what we can do is we can have a method like this. We can say print color rectangle R. So we pass in a rectangle, which could be anything that implements rectangle. And then we can say if R instance of, we'll do the deconstruction pattern with color rectangle. So color rectangle has two color points, top left and bottom right. Then what we can do is we can print out top left.c to print out the color of that top left corner. But top left is a record as well. So we can compose our record patterns and we can end up with something like this. So we can say if our instance of color rectangle, and then give the record definition of that, but we can include in that our first parameter as a color point and give it the record definition, point P, color C, and then the second value in the color rectangle is the bottom right, which I've shortened to BR here, and then we can simply print out color C as a single variable. We don't have to do the deconstruction ourselves. But of course, point P is a record, so we can go a little bit further. We can compose that even further, and we can end up with something like this. So if we wanted to print out the top left X of a rectangle, we say if our instance of color rectangle, which contains a color point as one of the record values, that in itself contains a point, and we give the definition of that double X double Y, and the color C, and the color point bottom right. And then if we just want to print out X, we can do that simply by referencing X. Obviously, at this point, you start to look at this and you think, I'm not sure of the value of that, because although we're doing deconstruction patterns and it's nice, it is making life quite complicated in terms of the readability of the code. We're introducing a lot of values, a lot of variables, and I'm actually only interested in one of those. So there's an awful lot of clutter around this, which makes it hard to understand what's going on. So we can do a couple of things there. First is we can use local variable type inference, which was introduced in JDK 10. So we could use var. Now we can shorten things and simply say, okay, we've got a color rectangle that contains a color point, which contains a point, and it's got X and Y in it. We don't care what those are. We'll just call them var. And then similarly for the color, we'll just call it var, and the bottom right, we'll call it var. So that shortens things a little bit and makes life a little bit easier, but it's still not a great way of doing things because, of course, we're hiding the type information and making it harder for us to understand what's going on in that code. So what we can do is we can actually use a new feature that came in JDK 21, released just this week, which is called unnamed pattern variables. What that allows us to do is to now eliminate the things that we're not interested in completely, and we simply replace all of that with a single underscore. So now we can say color rectangle, color point, point var X, which is the thing we actually want to use, but the second parameter of that record declaration, we're not using it, we don't care about it, so we'll replace it with an underscore. Again, the second variable in the declaration of color point we're not going to use, we don't care about it, we put an underscore, and the second variable in the color rectangle we don't care about, we put a single underscore there. That way the compiler knows the structure of the record so it can match against what's available, but you don't have to look at those values and you can simply say, okay, print out the value of X. No interest in the underscores, it just makes life a little bit simpler. And if you look at JET 443, there's a little bit more to it than that, just more than unnamed pattern variables. It's quite an interesting one, so I recommend looking at that in more detail. Just briefly talk about named record patterns, because this was something that was part of the specification and has now been dropped, but it's worth exploring why it was available and why it's been dropped. So again, let's take an interface called shared point, and it's got a method which returns a Boolean called isShared. Then we'll go back to our point example and we'll create two different versions of point. We'll have point2d, which takes an X and a Y, implements shared point, and has the method isShared, which returns true. Similarly, we'll create a 3D point, which has an X, Y, and a Z, implements shared point, has an implementation of isShared, and returns true. Now, what we could do is something like this, where we've got a switch where we're using pattern matching on switch, and we can say, right, so we've got a shared point that we're passing in, we're going to switch on S, case point to D, and we define the record descriptor, so it's double X and double Y, we can print out the value of X. In the case point 3D, we've got another deconstruction pattern, we've got the record declaration, double X, double Y, double Z, and we print out the Z value, and we've got a default. Okay, so that works nicely. But what we might want to do is to combine the deconstruction pattern with a record or a pattern variable for the type, which is a record. What I mean by that is we could say case point 2D, double X double Y is the record declaration, but we also want a reference to the point itself, so we could call the isShared method on that. So that makes perfect sense, very logical. So now we can print out isShared and the X value. The problem comes when we use a guard, because if we do this, we say double X double Y P when P is shared, then we want to print out isShared plus X. Okay. That will still work. The compiler can still evaluate all of that and say, yes, we understand what's going on. But we can just go a little bit further and we can do this. This is horrible. Let's introduce a local method called when that takes a Boolean. Now what we can do is we can legitimately say case point2d, where we've got the record declaration with two doubles, x and y, and then we're going to say when true. If we look at that, the compiler can come up with two different perfectly legitimate ways of interpreting that. The first way of interpreting it is to say that the first when is the pattern variable. So we are saying that point2d will be assigned the pattern variable when that we want to reference. As you can see, when is shared. And the second when is going to be the fact that it is a guarded pattern. So the right-hand side of that when is what we're evaluating to see whether it matches the guarded pattern. Because it's true in brackets, it will always evaluate as true, so it matches. So that's fine. The second way we could interpret it is that the first when is actually the guard, and then the second when is a call to that local method you can see down below with the value true. So which is it? Is it the first where we use the first when as a pattern variable, or is it the second where the first when is a guard? We don't know. So the compiler must reject that code. So essentially what happened was that the developers of this feature decided that they would not allow named record patterns where you could provide a record with pattern variable as well as a deconstruction pattern. I think this would have been better. My personal opinion, I'm just spouting here, but I think if we stuck to the case of using double ampersand, the AND operator in Java, this would never have been a problem, and we could have then used pattern named record patterns as well as deconstruction patterns. So this is what you see. You find that the compiler will just reject it. So those were taken out in JDK 20. Right, last thing to mention is a thing that isn't in Java yet, but could be at some point in the future. There was a JEP for this, but it hasn't been actually included. This is another example of a deconstruction pattern where we can do the same thing for arrays. We can use instance of, and remember that we can use arrays of either primitives or we can use arrays of objects. So here I'm saying if O instance of string array, and we'll give it a pattern variable of SA, then we're going to use a guarded pattern here, which actually I should use when there. That's an error. So I should use when there. SA.length is greater than equal to 2. So if we've got 2 or more elements in our array, then we can deconstruct it by saying, okay, string S1 equals SA0, string S2 equals SA1, and then we'll print out the value S1 plus S2. So what we could potentially do is decompose it by using this, where we'd say if O instance of string array, and then we use the way of declaring or initializing a string array. And so we'll use the curly braces and say string S1, string S2 to reference the variables we want in there. Because there could be multiple other elements in that array, we'll use the ellipsis, which is effectively var args there. And then we could say system.out println S1 plus S2. So it's a deconstruction. As I say, that's not included in Java yet. It may be at some point in the future. That was JEP 405, as I said. Okay, just to summarize then, pattern matching is a very powerful set of language constructs, and it does simplify a number of different tasks. If you look at the examples that I've shown you, you could argue, yes, less boilerplate code in most of those. There are some that I've shown you which are bad examples. Don't do those things like when. Be careful of those types of things. It is a lot more concise in terms of how you can declare certain things. It's more declarative in the way that it works. It's all very good. Also has the potential underneath for better optimization of the code and enhanced performance. That's not something I've talked about here because I didn't have time, but effectively the way that the compiler can compile the code, we could get better performance for certain things that are happening in that sense. Many features, as we've seen already included, you can expect to see some more later because I know that there are other ideas for how we can further pattern matching in Java. So with that, I'll say that's the end of the presentation, and thank you very much. So I have managed to bring in a few minutes on the call, so I'm not sure what we're doing now.
Yeah, thank you, Simon. Yeah, I mean, we were like, I would say, perfectly on timing. And you basically saved a couple of minutes. But the good thing is that we have the break after the next session, so we can
Okay.
actually like come back to the original schedule. So which is good. And yeah, I mean, thanks a lot for the interesting presentation as always. You know, I didn't. I didn't think that the pattern matching is so the big topic actually, and there are like more and more enhancement that we can do, which is like amazing. So yeah, I mean, thank you very much,
It
and
is
then of course,
interesting when you get to all the edge cases and trying to understand all the different like,
yeah,
aspects of it. The sort of basic ideas, you're just
yeah,
using pattern, instance of string
and
S type thing. That's quite simple.
and
But when you get into all the edge cases, it does
yeah,
get a lot more interesting.
and if you think about the all crazy ways what people can do and kind of bastardize the features, right? I mean, it becomes the
That's what I do.
nightmare for the developers, the
Yeah, hopefully
platform
I've shown you what
developers.
not to do as well as
Cool.
what to do.
Yeah, yeah. No, that was a good tip. Okay, thank you, Simon. Was a
Great.
pleasure to have you
It has
with
been a
us.
real pleasure to take part in this. Thank you so much for inviting me.
Thank you. Cheers. Take care.
Bye bye.